I introduced you using, oh my God, so let me record. Thank you. So I'm going to begin to record now.
This meeting is being recorded.
Okay, so hi everybody again. Good to see all of you. So before I move to today's material, let me kind of tell us where we are, what we have done so far. And I'm definitely sure I'll forget a few things. And if I do, somebody please remind me, okay? All right. So far, we got introduced to this class. I began by discussing the all the the usual properties of financial time series. I posted all of them on Blackboard. I gave you a couple of articles there. We saw some properties, volatility bunching together and clusters. And we saw, some heteroscedasticity. We saw a few. We saw leverage effects. We saw many effects. Okay, so 11 of them we discussed. And then I introduced us to the idea behind the moments of a distribution. Okay, and I said the moments of a distribution are, the characteristics of any distribution. So if for our purposes, we usually focus on 4 moments: mean, variance, skewness, kurtosis. So we discussed all of that, and that led us to why do we discuss moments? Because typically we want to see whether the distribution, what kind of distribution we have. And the simplest kind of distributions we want to work with is the normal distribution. So that led us to defining the normal distribution as one for which the skewness and the excess kurtosis will be 0, okay? And therefore, a formal, you can test that, you can eyeball that using the QQ test. I didn't make a big deal about that. Or a very formal test is, you can eyeball that using the QQ diagram, but a very formal test is the Jacques-Bera test. So we saw how we do that. And then in chapter 1, we introduced the concept of R as the tool we use this semester instead of Excel. So, well, in addition to Excel when we have to. And then we discussed, we downloaded some R programs, some R packages, in addition to the core R programs that comes with the program. On page 12 of your textbook, those are the programs, XTS, QuantMod, and Zoo, I think, were the ones we began to work with. And within Zoo, there are many sub packages, and within XTS and so on. All right, so we discussed all of that. We discussed the idea of using QuantMod to get data because it helps us. You can go anywhere, Fred, you can go to Yahoo, you can go to government. So you can go many places to get data. So that's chapter 1. Okay, am I forgetting anything in chapter 1? Does anybody remember something we did that I did not mention for chapter 1? Okay, so that's pretty much it. And then other little things, graphing and F basics and all that. Okay. And then in chapter 2, I began chapter 2 by introducing the concept of stationarity. And we discussed, I give the characteristics of stationarity, why it's important, and how do we recognize stationarity. Okay, a number of properties. Again, I will review again later, but we mentioned stationarity. At that time, I introduced the concept of testing for stationarity, testing for serial correlation using the portmanteau tests. And then we spent quite some time on stationarity in that sense before I introduced the formal test for stationarity in terms of unit root, okay? But before then, we looked at a way to eyeball whether we have stationary processes or not is you can introduce the autocovariances and autocorrelations. So we went over that, we did some Excel stuff, and then we got introduced to the ACF, the autocorrelation function. And the ACF is really a diagram that helps you and I to eyeball. to see how autocorrelation at each lag, what values they take, okay? And positive or negative. And then if we are considering not just one lag, for example, I have Microsoft for many years, and I'm looking at daily data or monthly data. Month 1 and month 2 are separated by one lag. Month 2 and month 3 separated by one lag. Month 90 and month 91 separated by one lag. So that's lag 1. Then month 1 and month 3, 2 and 4, those are 2 lags, and so on. So if we could calculate the correlation between observations separated by one lag, that's the autocorrelation at lag 1. If we can calculate the correlation between observations separated by 2 lags, that's autocorrelation at lag 2, lag 3, lag 4, and so on. So if you can do all those autocorrelations and plot the autocorrelation on the vertical axis and the lags on the horizontal axis and join them or not join them, that diagram is called the ACF, the autocorrelation function. You can also calculate something we call the partial autocorrelation function. I didn't go into that in this class. It's just a mess. To calculate partial autocorrelations is a complete mess. I didn't go into that. We didn't have time. But bottom line is you can draw the ACF, you can draw the PACF, and then you can eyeball to see what's the shape of the graphs. And with the shape of the graphs, you can make some tentative, very tentative conclusions. And then whatever conclusions we make, you can then go and do formal tests. So again, the way I look at ACF is the way I look at QQ tests, not QQ tests, QQ diagrams. QQ diagrams, again, we should have caught up with QQ diagrams in statistics or ECHO 4000, but if you didn't, don't worry about it. QQ diagrams are things you can use to see whether, you know, a sample comes from a normal distribution, because you draw what we call the quartiles of the sample and the quartiles of a normal distribution. If the sample happens to come from a normal distribution and you draw it against the quartiles of a normal distribution, the QQ diagram will be exactly a straight line. All the points of your Microsoft will plot, all the quartiles will plot on a straight line starting from the origin. But sometimes you do that, you are not quite sure. So what do? You do the Jacques-Berra test. So the Jacques-Berra test is a statistical test that tells us, you know, yes or no. The same way, if you look at the ACF and the PACF, the ACF and the PACF, we know what they should look like for white noise. We know what they should look like for other processes. Okay, and then the PACF. But sometimes you draw them, you're not really quite sure. Sometimes you draw, you're pretty sure. Sometimes you draw them, you're not quite sure. So what do? You go and do some other tests. Okay, all right. So we introduce the ACF and the PACF as a way of initially figuring out what kind of processes we have. What kind of processes are possible? We introduce ourselves to the white noise processes. The fundamental white noise process, they are just processes that are well behaved, okay? Zero mean, the mean can be constant, the mean can be zero, but it's just a kind of a process that is so clean. It's like you're an artist, you know, I give you your brush, I give you your colors, and I give you a blank canvas. And I say, now begin to draw. So you can think of a white noise process as that blank canvas, okay? It's the most fundamental, okay? And those of you who are going to study, who have studied options, it's like beginning with the Black-Scholes option pricing model. It's just the basic, okay? And then from there, we can build onto other models. So beginning with the white noise process, then we introduce a white noise process has no trend, has no cycle, has no season, only irregular components. So it's just fundamental. It has no complications. If you plot a white noise process, there should be no trend. There should be no long cycles. There should be no season. Just plain irregular. Okay. So we introduce ourselves to autoregressive. What is autoregressive? Well, autoregressive is, the process, if it's IBM return. IBM return today is IBM return yesterday, a proportion of IBM's returns yesterday plus white noise. Okay, IBM's return tomorrow is some fraction phi, some fraction 0.5, 0.6, 0.8, some fraction of IBM's return the day before today, plus white noise error process. So autoregressive meaning, the observation of the process today is equal to some white noise process plus a fraction of what we observed yesterday. Today's return for IBM is a fraction of yesterday's return plus white noise. So that's what an autoregressive process is. And we saw that an autoregressive process, how can we through eyeballing, identify maybe it's an autoregressive process? Number one, look at the ACF. The ACF should be declining exponentially. If the coefficients are positive, it should be declining. If the coefficients are negative, then it's kind of rising from below zero, rising up. If that happens, we say, oh, by the way, this could be white noise. No, I'm sorry, this could be an AR process. But if it's an AR process, how many lags does it last? Today's observation of the return to IBM, how far back should we go to observe the return plus white noise to make today's return? That's lags. How do we determine the lags for AR process? We look at the PACF. For the PACF, where the partial autocorrelations are the lags, where they break through the barrier. Okay, if it's an AR1 process, the line will break through the confidence band at lag 1, and everywhere else should be 0. They will not break through, not 0. The lines will not break through the bounds. If it's an AR3 process, then you look at the ACF, it should be declining. You look at the PACF, it should be vertical bars breaking through the confidence bands at the first 3 lags, and then in lag 4, 5, and so on, they will be within the bounds. That would be neatly an AR3. So we studied all of that. And then we looked at the issue of how do we really determine if we're not quite sure, if the PACF doesn't really help us that much, and we're not sure whether it's an AR1 process or AR3 process or AR5 process or AR7 process, no sweat. Use them all. Estimate them all and look at their AIC or BIC. Look at the information criterion. And we typically will look at the AIC because it is less restrictive. Okay, but you can do BIC or Hanan Quinn. I didn't show you the HQ information criterion because it wasn't discussed in your book. But either one, if you want to work with BIC, stick with BIC. If you want to work with AIC, stick with AIC. So if you apply the information criteria, then the model, either if you're not sure which model it is, then the model that gives you the smallest positive AIC or the largest negative AIC is a kosher one, is the correct one. Okay, so we saw that. What else did we see? Am I missing out on something in chapter 2? Anybody?
Professor, I just want to get some clarification. So,
Danny, yes.
Are you saying that autoregressive models aren't white noise? Because I thought that autoregressive models needed to have a constant variance, which
yes, those properties hold. But autoregressive models are not white noise. Autoregressive processes usually, remember, an autoregressive model says that the return today for IBM is equal to, let's say the constant is 0. Let's say the constant term is 0. So it means we're saying, for example, the return to IBM today, time t today, is equal to maybe 0.8 times yesterday's return to IBM, right? Plus a white noise.
Correct.
It's not white noise. It's a function of a white noise. It's something plus a white noise. That's very important because I'm going to introduce you to moving average today. So Danny, that's a very important question you asked, and I hope everybody understands it. XT equal to phi xt minus 1 plus ut. Ut is the white noise. If xt equals nothing but xt equals ut, that's a white noise. But then that's not autoregressive. How do we know it's autoregressive? Because itself regressed 1 lag or 2 lags. So xt equals some constant times, that's phi times xt minus 1. That's the autoregressive part, plus the white noise.
So the first product of that equation is the drift, right? I'm getting that right?
No, what do you mean by the first product?
Like the phi times the xt minus 1.
That's the autoregressive component. That's not the drift.
Okay.
The drift is if I have xt equal to 1.2 plus 0.8 xt minus 1. That 1.2 would be the drift. So the drift is the constant that, Danny, the constant that we usually put to 0 when we do our proofs, right?
Yeah.
That's what we call the drift. Okay?
Okay.
My proof, that's the one I call mu at the beginning. But I said it complicates our proof. So usually I say, let us prove this with a 0 constant AR process. If that constant were not 0, if it's a number, that number is the drift. Okay? All right. Okay. So so where was I? Yes, so you get that, right, Danny?
Yes, that would be a 0 mean autoregressive of order 1, right?
Yes.
What you
Yes.
just gave, the example you gave? Okay.
Yes, with no drift, right?
No drift.
Okay, excellent. All right. So anything else I missed?
But AR0 is white noise because it doesn't have the X.
Yeah, you can say
component.
AR0 is white noise, but I don't like to do that because it can confuse you. Okay, I don't like to do that. If you want to say white noise, just say white noise. That's why I suggested for Roxolana to go ahead and test formally for white noise. Okay?
Yeah.
You can, yes, you can get away with saying AR0 is white noise. I just don't like that because it's confusing. Just say white noise.
But there's cases where it's not, right? And that's where you do the testing.
Yes, there are many cases where it may not be, depending on what else is added to the white noise.
Like the drift, right?
Like the drift, like the trend. There could be trend, there could be drift, there could be deterministic trend, there could be stochastic trend, there could be a bunch of many things. So I just don't like that. Okay?
No,
Yeah, it makes me nervous when my students at this level say it's white noise. No, but I cannot go into many details. I mean, there are so many things that can be added to the white noise that will make it not white noise. You see what I'm saying? All right. Okay. So that's why I suggested for Roxolana to go ahead and test for white noise. And if it is white noise, then you can say categorically it is white noise with authority. Okay. So that's where I think many other distractions in the class. We did R programming. We introduced the Pearson, the Spearman, the Kendall. So many other things, so many other issues came up. Okay. So those are all in chapter 2. So, but tonight, I want to impress on us that, look, the AR model is not the only type of model in time series. There are millions of them. But out of those millions, a huge proportion of them belong to the family called autoregressive models. But there's another family called moving average models, MA. Okay? So again, if you understand the concept behind autoregressive models, all the like the properties and the ACFs and so on, then I'm just going to introduce us to the MA, just point at some things. That's what I'm going to do tonight, okay? But the intuition should be the same. All right. So if you haven't done that, please go to your Blackboard. I put 2 pages of moving average and then 1 page of ARMA. So I'm going to bring it up right now, and I'll just point you through and you know, kind of talk you through those. And feel free to stop me anytime, okay? Okay. Please, somebody tell me you can see this.
Yep.
Okay. Okay, thank you. Everything I say, you have it on Blackboard, okay? So the moving average, remember when we want to discuss the autoregression, we usually say an AR parenthesis P. So whenever you discuss AR, if it's AR1, then P equal to 1. So P is the order of an AR process. For MA models, we don't use P, we use Q. I mean, I don't know why, but that's the tradition in the discipline. So I don't say MAP. No, I say ARP and MAQ. So the Q will tell me whether it's an MA one moving average of order 1 or moving average of order 2, and so on and so forth. Okay. So the general structure here, please look carefully at this one. The general structure is that XT. So if I want to check whether, so I go to Yahoo, I download Facebook, and I want to check, is that Facebook an AR process or an MA process? If it's an MA moving average process, then it should take this structure, okay? It should be the return to Facebook or IBM or whatever is at today, at the particular time, is equal to some constant, okay? Some constant, Danny, this is what you can call the drift, some constant, plus, look, from here on, this thing I use, I don't like using mu because it's a little confusing with u, but your textbooks tend to stick on mu. When I learned this, I didn't use mu, but many of the books you will see use mu. So that's why, but look, it's a long tail mu, u. But, so that's the constant. But look, everything else here, everything else is a white noise process, it's a u. So a moving average, look, if this mu, this constant is 0, right? Danny, you're watching? Just following up on your question. If this constant is 0, then a moving average process is really a combination of white noise processes. Okay? So
Professor, can you please repeat that?
Okay, Alec, that's you, right?
Yes.
Okay. So just follow the cursor here. X sub t, think of it as the return at time t. Let's say today's return to Facebook. So you calculate simple returns, and today's return is equal to some constant. Let's say 1.2 or 0.5, some constant, plus, look, ut minus 1, ut minus 2, up to ut minus q. All these u's, they are white noise processes. You see that, Alec? All these u's are white. So in other words, a moving average process is really a bunch of white noise processes added together. This ut is a white noise today. It's an error, just like in your OLS regression. The error epsilon at the end of the equation for today. That's today's error, plus a fraction of yesterday's error, plus a fraction of the error from 2 days ago, plus a fraction of the error from many days ago, depending on what the Q is, depending on what the order is. Okay, Alec? So it's, in other words, if you remove this first term, the constant here, if it's a zero constant moving average, zero, that constant is zero. Then what is this process really? A bunch of white noise processes. You see that? It's many processes added together. Many white noise processes added together. Okay? So, okay, let me not say this now. Maybe in the future I'll say it because I don't want to confuse you. But what is a white noise process? A white noise process is an error term that you cannot predict. Think of OLS. Think of your Echo 4000 when you want to run a regression. Y equals A plus BX, and then at the end, you tag on that little epsilon. That epsilon, if it's not predictable, if it doesn't have a structure, if there's, that's what we call a white noise. Okay? But a moving average process is not only one epsilon. It's not today's error process. So we're saying that if you take whatever the error is today, you add maybe 80% of yesterday's error. So this first theta 1 will be 0.8. So suppose this mu constant is 0, then I'm saying Facebook's return today is determined by today's error, epsilon, or U, white noise process, plus 80% of yesterday's error, if this is 0.8, if this is 0.5, plus 50% of the error from 2 days ago, from to 20% of the error 5 days ago. So it's just a bunch of errors added together. That's what a moving average process is. Okay, somebody is chatting. He said that because your mic cut out for a bit. Okay. Okay. Any questions? Anybody misunderstanding me? All right. Okay, so that's what a moving average process is. It's really a look here. A moving average process is a linear combination of white noise processes. That's exactly what I just explained. So it says that XT, that is the return today to IBM or Facebook or Microsoft, depends on the current and previous values of a white noise error term. That's what it is. Okay? So look, XT equal to this constant plus a bunch of errors and their relations, linear combinations, plus today's errors. So a bunch of previous errors plus today's error. That's what a moving average process is. Let me just wait here. Somebody in this class must have a question about this. So any questions, anybody? It doesn't matter where that question is coming from, right field, front field, back field, left field. Ask me any questions so far.
So, Professor.
Yes, sir.
So from what equation does this white noise UT come from?
Okay. Whew. Which equation? The XT, this first one?
No. So the error term is a residual that comes from
Fantastic.
us making an assumption on some, let's say, some return of IBM stock, right?
Okay, so
yeah,
Alec,
that's my question.
Alec, thank you. Okay, just again, how many beers do I owe you, or how many coffees do I owe you already?
Zero, as long as you give me an A, Professor.
All right. So whatever I owe you, add one more to it, okay? Because this question allows me to explain what this truly is, okay? Thank you. So let's just say today is the first day of the beginning of the world, okay, everybody? Today is the beginning of the world. All right. So today is T equal to 0. Clean, slate, the world begins today. And then you and I will say, okay, let us predict what IBM's return will be tomorrow. That's a prediction. It's a prediction. It's a prediction. Nobody knows tomorrow. None of us knows tomorrow. So we say, okay, tomorrow, so as of today, we make a prediction for what we think IBM's return will be tomorrow. Let's say we say tomorrow, based on all our voodoo and nuclear science, whatever mathematical model you use, you predict. And we all agree is tomorrow IBM will give us 8% return. That's a prediction we made today, conditioned on all the information we have today. And then tomorrow, what happens? 4 p.m., when does the market close? Whatever, 4 p.m., 4:05, we measure IBM's return for tomorrow. What is it? 10%. What mistake did we make? What error did we make? 2, right? Yes?
Yes.
10, yes, 10 minus 8. We predicted 8, we got 10. So we made a mistake of 2. That mistake is the error, residual, whatever you call it, whatever, in this simple example, okay? So for tomorrow, we made 2%. So come tomorrow, we made 2% return. Yeah, Danny?
I feel like you're confusing me with the dates because wouldn't that be t plus 1, ut plus 1?
Yes, so
Right.
today, let's say today T is 0. Tomorrow is T1,
It would
T
be
plus
t
1,
plus 1.
whatever. So T plus 1, but T is 0 plus 1 is 1, right? So tomorrow is time 1. Okay, T plus 1, that's fine. Okay, Danny, I don't want to lose you.
You could carry on. I'll just rewatch it.
Okay, so think about today as times 0, okay? So T equal to 0 today, times 0. Tomorrow is T plus 1, which is 0 plus 1, that's time 1. So tomorrow is tomorrow, 1 day. And we make a mistake of 2%, okay? So our error. So let's move on to tomorrow. We observe the actual return for IBM is 10%, but we had predicted 8%. So our error is 2, okay, in my example, right? Alec, you're keeping track. So for tomorrow, the error we made is 2. And then tomorrow, we make prediction for 2 days from now. So we predict that, remember, at T1, the return is 10%. But at T1, we make a prediction for T2. And suppose we predicted for T2 that the thing would be 6% for T2. But then at T2, we made 4%. So the error is minus 2. So at T1, the error is plus 2. At T2, the error is minus 2. And then at T2, we make a prediction for T3. Are you with me? Now, what guides us in predicting for T3? We might say, look, for T3, let us predict that the return on T3 will be the error for T2 plus 80% of the error for T1. You understand, Alec?
Yes.
Because we are saying that, yes, the error we make at each time period is a great information. At T1, we made a prediction of 8%, but we got 10%, so we under-predicted. At T2, we made a prediction for 6%, and then we made actual return of 4%, so we over-predicted. So we're saying to predict about
Caution
ut minus
about
1.
T.
I just said error. Okay, so you're calling it ut minus 1. So what's your problem, Daniel? What's your question, I mean?
Well, it's the same thing as Alex's. I don't see how that explains the UT, the second variable.
Which one? This ut? This one, huh?
Yeah, because isn't that like the same date as XT? So how would you get that?
Okay, so let me explain it again, okay? Let's start again today, right? Are you with me today? Danny?
Yeah,
Okay, so today, xt. Today, t is 0. So there's nothing going on today, all right? Today is the beginning of life. Are you with me? I need to hear you.
it's just that part confuses me because it says T minus 1. So why are you using, there's no negative.
Yes,
data.
so if life begins today, what is t minus 1? Nothing.
Exactly. So can we start at T equals 10?
No. Let's start at t equal to 0, because then time minus 1 never existed. All right? We just started life today.
Okay.
You're thinking too deeply, Danny. Okay,
It's just,
but
I'm looking at the equation. It doesn't make
yeah,
sense.
but that's okay. But look at the equation, but let's think about this, okay? Today life begins. So there was no yesterday.
Yeah.
Okay, there was no yesterday. So I mean, just if this was a class on financial economics, when we do proofs, you get used to it, because it's just something you have to accept. Today is the beginning of life. There was no yesterday. We are created today, no yesterday. But when we move on to tomorrow, then when we get to tomorrow, what's yesterday? What's t minus 1? That's today. We're starting today. Are you with me so far? Yes?
Yeah.
Okay. So tomorrow, so as of today, we make a prediction. So we are born today, we are smart, all of us are smart, we're okay. So today is the first day of life. And then we say, hey guys, predict for what IBM's return will be tomorrow. And all of us, we agree, maybe we fight initially, but at the end we agree that IBM's return tomorrow will be 8%. Okay, Danny, can you accept that from me?
Yeah.
Okay, so we all predict today, we say we believe to the best of our knowledge that tomorrow we should expect IBM's return to be 8%. So we go to bed today, we wake up tomorrow, and then the trading happens, and at 4 p.m. the market closes. And I say, Danny, what was IBM's return for that's tomorrow?
10.
Remember, tomorrow we're looking for XT. IBM's return tomorrow is XT for tomorrow. All right, but T tomorrow is T1. Okay, T equals 1. So X1 tomorrow will be equal to, okay, and then you tell me that IBM actually returned 10%, because the market already closed when you checked. Huh? 10%, but yesterday, but the day before, we predicted 8%. So what error did we make? We made an error of 2, 10 minus 8. Are you with me?
Yeah.
So, but as of tomorrow, XT, the error we made tomorrow is 2%. So that is this UT, because it's the same time period. Okay, coming from yesterday to today, we made the error. Okay, what is this T minus 1? Well, the error we made at time 0, we didn't make an error because today time 0 was the beginning of life. So all these other things are not part of the equation, because we didn't make an error yesterday because life just started. Okay, so as of tomorrow, we make prediction for 2 days from now. Okay, that's at X2. So as of tomorrow, X1, we make prediction for X2. Let's say we predicted, let me use positive, we predicted 14%. And on day 2, you check, the return was 11%. So the error in day 2, this UT in day 2 will be 14 minus 11, that's 3. Plus, now in time 3, we have a previous error. The previous error was 2. So we say, you know, voila, let's see if we can predict day 4 with the errors, because the errors will give us a message. But on day 4, we use the 3's error plus the 2's error plus the 1's error and so on and so forth for whatever error we have available to us. That's what a moving average process is. We are not focusing on the return. If on day 4, I say, let's predict for day 4, that the return on day 4 will be equal to a certain proportion of the return to day 3. That's an autoregressive process. Because I'm saying return xt on day 4 will be equal to some proportion of return to day 3. So I have return on the left-hand side, I have return on the right-hand side. That's an autoregressive process. But for moving average process, I don't have return on the right-hand side. I just have the errors. Error on that day, error the previous day, error the 2 days later. That's what a moving average process is, okay? I will revisit this. Don't worry, if you don't get it today, I'll keep coming back to it until we get it, okay? Don't worry about it. All right, so look at the properties. Remember, for autoregressive model, I spent like 7 pages of handwritten notes proving those characteristics and the properties. But here I won't prove it because it will take me like 15 pages to prove. But you have to accept this from me. It's in your textbook. It's ugly the way your textbook stated it, but your textbook states it. But I just kind of summarized it by right. Please forgive my handwriting, okay? It took me a long time to write because I'm not this neat. So properties of an ME model. Look, guys, the average, the first moment, the average for a moving average process is equal to this constant. And if this constant is 0, then what will be the average? Is 0. Okay, everyone? What is the variance? The variance is, remember, the variance is the same as the autocovariance at lag 0. If you are not comfortable with this, I just ask you to remember all the proofs, the 7-page proofs I gave you, I hand wrote and I uploaded on Blackboard. Remember, our gamma is what we use to represent the autocovariance, and the autocovariance, when lag is 0, the autocovariance at lag 0 is the same thing as the variance. We went through that already. And if I go through an elaborate 3-4 page proof, like I did for, maybe not 3-4 pages, maybe 2 pages, like I did for the autoregressive model, AR model, you will see that this is the relationship. Oh, before I forget, let me move back up. Look, each of these white noise processes, they are all white noise. That is on this box here. UT is white noise. So anywhere you see UT, UT minus 1, UT minus 2, UT minus Q is white noise. And the expected value of the white noise process is 0, and it is homoscedastic. Look, guys, same thing from Echo 4000. Okay, the average is like, remember, Alec, in Echo 4000, the epsilon, the error was mean 0, constant variance, or what you call homoscedasticity. You remember that, right?
Yes.
Okay, now, Alec, hang in there, don't cut me off yet. Look, what happens if I come in here, all right? Under this variance, you see there's nothing here. What happens if I tag on a little t here underneath? What happens? Is it now homoscedastic? If I put sigma squared with time
Yes.
here.
Yes.
No, with time.
Oh,
with time. Time is changing. That means the variance will be changing with the
so
time.
that's heteroscedastic, right?
Fantastic. Fantastic. Look, what does homoscedastic mean? It means that if this variance is 12, right? That number stays the same. It doesn't matter where along the process we are. If you get Microsoft, and you have 50 years of daily data or monthly data, it doesn't matter where you are, the variance of that error term will be 12. It doesn't matter whether you turn left or turn right, up and down, the variance will be 12. Are you with me?
Yes.
The variance of that error term will be 12. But if I stick in a little t here, what does it mean? It depends on the time period you are considering. The variance can be 12 in this time period. In the middle time period could be 5. In the end time period could be 6. In the other time period could be 1. You understand? So the variance can change. Yes?
Yes.
Isn't homoscedastic?
No, that's
Finite?
heteroscedastic when it's changing. But let me finish now. But if something is changing, if I tell you something is changing, right? What is your next question to me? How is it changing? Is that right? Is it changing according to exponential? Or is it changing linearly? Or is it changing, like a sine wave? Or is it changing like a cosine wave? Are you with me? So whenever somebody tells me something is no longer constant, because look, if something is constant, look, guys, I don't know if you see, if something is constant, this is the line, right? Bingo, it's a constant line here, right? You see that? It's fixed, it's flat. That's what is constant. But if it's not constant, how can it be? It can trend upwards, or it can trend downward, or it can be a curve, or it can be cubic, or it can be sinusoidal, it can be cosine, it can be, so anytime anybody tells you that something is not constant, the next question you have to ask is like knee-jerk. Okay, it's not constant, that means it's changing. How is it changing? Is it changing linearly? Is it changing quadratically? Is it changing as cubic? Is it changing as this? Is it changing as that? That's what chapter 4 is all about. Because in chapter 4, we are saying, you see this constant term, this variance is no longer constant. So how is it changing? There are many, many ways variances can change. But there's a one particular way we call arch. There's another particular way we call gotch. That's what we're going to be introducing in chapter 4. Variance is changing. So here, look, there's t. We add t here. But if you add t, it means it's no longer homoscedastic, it's heteroscedastic. But what is the nature of the heteroscedasticity? How is it changing? What equation can I use? Is it a linear equation? Is it a quadratic equation? Is it a, pi type change? I mean, there are many types of changes. How does it change is what we're going to be talking about. Okay, so let me come back to now. Danny, what's your question?
What if the change isn't like something that you could like formulate that's like linear or quadratic?
Yeah, we shall see that in chapter 4. Believe me, that's what we shall do in chapter 4, okay? Just hold on to it, okay? That's a great question.
Isn't
But
the
how-
homoscedastic also finite? Like, isn't homoscedastic within a range? Like,
Yes. If
not
we say
only
if we say the variance is constant and finite, everything we are talking about in this class, the variance is constant and finite. Finite meaning it's not infinity. It's not some ridiculous thing.
so it's within a range.
Yes, it is within. It's a number we know.
Yeah.
What the heck is infinity or infinity minus 1? That's nothing. So we're saying nothing that crazy. You understand?
Yeah, but it's not necessarily the same number at all intervals, right?
It is the same number at all intervals when we say it is homoscedastic. It's absolutely the same number. Danny, you beat me up, it's the same number. You make me happy, it's the same number. You make me sad, it's the same number. It doesn't matter what you say to me, I'll keep telling you, Danny, it's the same number. That's homoscedasticity. I mean, these concepts are very, you see, I like the way you guys are at echo 4000 level. You know, it's just, let's just do this and get rid of this. But later, if you really think about this concept, they are very deep. Okay, they are really deep. What do we mean by the variance stays constant forever? Does that even make sense? No, it doesn't make sense. That's why some of these models, when you apply them in practice, you have to make many, many adjustments. So all of us go to Excel and we run OLS without thinking. But if you really sat back and say, what assumptions are we making to use this regression model? Does it make sense? It doesn't make sense in many cases. All right. Okay, so why did I bring us back here? Because this homoscedastic variance, it appears in the property here, okay? You see, so we're saying the mean of the moving average process is equal to that constant. If the constant is 0, then the mean of the returns to IBM, whatever, the mean of the moving average process is equal to 0. What is the variance? The variance is, again, the autocovariance at lag 0, and is given by this 1 plus the constant to the first, the constant 1, constant 2, up to constant to the order of the MA, times the variance of the white noise process, that homoscedastic variance. What are these things? Theta 1, theta 2, theta 3. What are they? Look here. Theta 1 is the coefficient. Hold on, is the coefficient attached to the lag error 1. Theta 2 is the coefficient attached to the lag error 2. What is the coefficient? Can anybody tell me what is the coefficient attached to this contemporaneous white noise process, the same time as,
It's 1 for
it's
UT.
It's exactly 1. That's why, look, we begin here with 1. You see that? So it's 1 plus this, plus this, plus this, plus this, okay? All right. Somebody had their hands raised. Who is that? Roxalana, that's you, yeah?
Yeah, I just have a question. So in the other model that we did, AR, we used phi, but here we use theta.
Yes, that is the convention, okay?
Okay, just wanted to clarify.
Yes, thank you for that. So in my mind, I just call them all constants. And then when I have to do some serious work, then I distinguish between phi and theta, all right? In some other models, they use omega. I mean, so you just have to keep track of what books are saying, but the more general coefficients to use are phi generally for AR and theta generally for moving average. Okay, somebody else had their hand raised. I can't see all of you at the same time. All right, and then the covariances. The covariances will be depending on how many lags we're talking about, okay? If it's a moving average, if it's an MA1 process, then Q is 1. If it's an MA2, Q is 2. If it's an MA10, then Q is 10. But S, we use S for different lags. So S can be lag 1, lag 2, lag 3. So if my order is 10, if I have a moving average, if this, look, this MAQ is an MA10 model, Q is 10, then I'll consider lag 1, lag 2, lag 3, lag 4, up to lag 10. So S is the many lags leading up to the number Q. Okay, so if I have a moving average 2, MA2, so Q is 2, then I'll only consider lags 1 and lag 2. If I have a moving average 4, MA, Q is 4, then my S will be 1, 2, 3, and then up to 4. All right, so covariance is equal to theta S, gamma S, which is the covariance. Remember, by definition, covariance is covariance between X and Y, or between XT and XT separated by a lag. So remember for covariance, we consider covariance xt and xt minus 1, covariance xt and xt minus 2, xt and xt minus 3, and so on and so forth, up to the order of the moving average q. Okay, so we notice, so if you go through the proof, okay, if you go, I mean, over the summer, again, call me, come to Baruch. I'm buying for coffee, or if you can tolerate beer or 1 glass of wine, don't worry about it. Just call me, come by, but try it before you come by. Try to do these proofs yourself, and then I can take like 1 hour. We go downstairs to the cafeteria or to the bookstore. My God, I look forward to that. And then I buy you coffee, and then we talk. Okay, but you can try this yourself. But if you prove this correctly, then your covariance could be one of 2 things. If, remember, these are autocovariances, and then on the second page, I'm going to change them. I'm going to convert them to autocorrelations. Bottom line for an MA model is that the covariances and therefore the autocorrelations, because we're going to go from covariance to correlations. If we have an MA2 model, MA2, so Q is 2. If we have an MA2 model, then after 2, for lags of 3, 4, 5, 6, beyond 2, the autocovariances are 0 and the autocorrelations are 0. So in other words, if you're looking at autocovariances and autocorrelations for an MA process, if it's an MA2 process, after lag 2, every other autocorrelation will be 0. Every other autocovariance will be 0. After lag 2, everything will fall within the bounds, within the confidence bounds. But between lag 1 and lag 2, they will be not within the bounds. So the way to identify a moving average process, unlike an AR, remember an AR process, the way to identify the order is we look at the PACF, not the ACF. For an MA model, it's the reverse. The way we identify whether we have an MA1 or MA2 or MA3, we simply look at the ACF. And we see how many of those bars break through the confidence bounds. Okay, so it's the ACF for an MA is exactly how we use it. Is exactly how we use the PACF for an AR model. Okay, all right. So I know you will look at this after, but let's go to the other page. Okay, let's go to page 2. You have page 2 there. Just give me a second. I'll bring it up. All right, right here. Okay, so this is the second page. You all have it already on Blackboard. So I use an example. I said, for example, an MA2, a 0 constant MA2 process. Okay, look, Alec, here, I don't have that mean, okay? That constant term. So here I define the constant at times as 0. So if you look at the first page where we just came out of, Alec, you will see that that constant, that first term on the right-hand side is non-existent. So look, the daily return or the monthly return to IBM here is the same thing as the error at the same month plus a certain percentage of the error from the previous month plus a certain percentage of the error from 2 months ago. So the moving average process is just a combination of error terms. That's all. White noise. In this case, the order is 2. So I stop at, the 2 days ago or 2 months ago. The error 3 months ago doesn't impact the returns, today's returns. Okay, so the return to IBM at any particular day would be a combination of the white noise, the error term for that day, plus a certain maybe 80% of the white noise for the previous day or month, plus maybe 60% of the white noise for the two periods before that, lag 2. That's what an MA. If no, look, guys, just eyeball this. Do I have XT or XT minus 1 on the right-hand side? No. So that's not an autoregressive process. So here, so what are the properties from page 1 here? X of the average is 0 because this constant is 0. Remember from page 1, I said the expected value of the moving average process is equal to the constant, but in this case, the constant is 0. What is the variance for this 0, 0 constant and MA2? What is the constant? Is 1 plus the coefficient of the first lag error. The coefficient of today's error is 1. Remember that? This is 1. You guys told me that earlier on. The coefficient of the lagged white noise, lag 1 white noise is theta 1. Sorry if Roxolana, I'm sorry if I confuse you. This theta, sometimes I mix it up, but it's theta 1 squared plus theta 2 squared. Because we have only the Q is 2, so the error, I'm sorry, the variance will be the coefficient of this one contemporaneous error plus theta 1 for the first error, for yesterday's error, and then theta 2 for 2 days ago, all of them squared, okay? You could have said 1 squared plus this squared, but 1 squared is 1. And then all of them, you add them together, multiply them by, can anybody remind me what this thing is, the variance here? What is it? What is this sigma squared? Is the variance of what?
Of the white noise, but
Exactly, it's the variance of the white noise, okay? So you will be given that number. I haven't given you here. I'm just saying whatever number is given, that's the number to use. So in other words, square the coefficient, to get the variance of this moving average process, square the coefficient of this first one, which is 1, square the coefficient of this t minus 1 coefficient, this one, square the coefficient of this t minus 2 coefficient, add up all of them, multiply them by the variance of the white noise process. That is the variance of the moving average process. Somebody had a question? Okay. How about the covariances? Covariance will be covariance of today's return with lag 1 return. Covariance is the expected, covariance between this and lag 2, covariance between this and lag 3. So what is covariance between xt and xt? Xt equal to 0 and xt equal to 0. That is the variance. Is the variance.
oh yeah.
Okay, that's this one. Okay, the lag is 0. So covariance between x of t and x of t, the lag is 0. So that's this one. That's the variance. Covariance of today's return with yesterday's return or any other lag 1 return along the line is gamma 1 is given by this. Okay. Now, look, I beg you, all of you, when you have time this week, go to the first page of this. We just finished discussing the first page. I showed you the covariance formula, okay, on the first page. Just plug in the numbers, you will get this. And then covariance of x2, xt, and xt minus 2 lag 2, you will get this. I did it, so you should be able to do it. But how about the covariance between xt and xt minus 3? Well, this is an MA2. So if I go to S equal to 3, then S is already greater than Q. What should that covariance be? 0. And the autocorrelation, of course, will be 0 too. Because for any lag bigger than the order, if the order is 2, it's an MA2, any other lag, 3, 4, 5, the autocovariance is 0, or statistically, it should be within the confidence bound, okay? Just one more thing and I'll end, sorry. What is the autocorrelation? Autocorrelation is autocovariance divided by the variance. Autocorrelation at lag 0 is the variance divided by the variance. LEC is 1. or Daniel, whoever mentioned it before. Andrew, you're kind of quiet today. I didn't like that. Oh, yeah, okay, you should be sorry. And Lily, you're a little bit quiet too. I don't like that too. Okay.
I'm following.
All right, good. All right, so here at lag 1 is the autocovariance at lag 1 divided by the variance, okay? So the autocovariance is this, we obtained it up here, divided by the variance. You remember 1 plus this plus this. The only common term is the variance of the white noise. So you remove it and this, okay? And then at lag 2, the same, the autocovariance at lag 2 divided by the variance. That is this, we got it from here. And again, I advise you to go over this. And then you divide it by the variance, which is this one, up there on the first page. And then look, these two, the variance of the error of the white noise terms, they're common, they cancel out, and you have this. And then because it's an MA2, autocovariance and autocorrelation at any lag more than 2 is 0. Okay, guys? All right, I'm sorry I took a few more minutes of your time. All right, so on Thursday, I'll finish up all of this, and then the ARMA will go very quickly because it's really a combination of the AR and the MA, so it will go quickly. So I'll finish that on Thursday and maybe do a few minutes of R session to simulate an MA and an ARMA, something like that, just something simple. And then that will be the end, okay? All right. And then Roxalana or Lily, can you guys, remind me on Thursday, I need to announce some things for the rest of the semester, okay? Things that will take us to the rest of the semester. I want to discuss it in class first. That's number 1. Then number 2, anybody in this class, how many of you use the Mac? How many of you have been using the Mac for your homework? All right, can you guys, I beg you, forgive me for whatever I have done wrong to you. Forgive me, okay? Can you just send me an email telling me, Professor, I use a Mac, okay? Please, all of you in this class who use a Mac, I beg you, not now, after class, send me an email. Just tell me, Professor, nothing, just say, Professor, I use Mac. Or you don't even have to dialogue with me. Just say, Professor, Mac. Okay? I beg you, okay? Because I want to know how many of you use the Mac in this class, okay? Thank you, everybody. I'll see you on Thursday. Let me stop recording.
Did that affect our other code, or is it going to affect our code in the future?
No, nothing. I just want to identify, that's all.
Okay.
Okay, so let me stop recording. Thank you, guys, okay? Thank you for
The
your
recording
patience.
has stopped.
All right. I have some people to meet tonight. So, but before I go to the meeting, I'm going to stay for like 5 minutes and take quick questions, okay? So if you have questions, go ahead and ask me now. Bye, guys. The rest of you,
So
bye.
are we